All right, first, does anybody, when y'all were doing the outdoor observation lab this past week, does anybody have any cool observations that they recorded that they'd like to share with everyone? Does anybody just want to briefly share what they observed whenever they did the activity?
I observed that it was really, really cloudy whenever I did it.
Which day did you do the activity?
I did it last Thursday. So,
Okay.
yeah, all of my pictures were pretty much kind of the same.
Yeah, that's right when that cold front was coming through, so that's why it was cloudy that day.
Yeah, for sure.
Anybody else?
Um, can you hear me?
Yes.
My mic wasn't unmuting
Yeah,
earlier. Okay.
I can hear you.
I did my observation yesterday evening around 6:40-ish, and I mostly just saw cirrus clouds and a couple of like ragged stratus clouds, and I thought the wind was around 10 miles an hour, and it was a southeasterly wind.
Awesome. Yeah, and you mentioned the cirrus clouds, and if you remember from the slides that a lot of times cirrus clouds can be indicative of incoming weather patterns. So if you you might have noticed, depending on when you did the activity, if you looked at the forecast on the Weather Services site, there's another cold front coming at the end of this week in a couple days. So pretty cool how it like all lines up. So yeah, I hope y'all had fun with that. Normally, whenever we have in-person labs, we're able to do more stuff like that, but we're just trying to make the best of it this semester. All right, let's go ahead and get started with our new topic this week. So we are going to be doing weather map analysis. So this is just like the past couple of weeks, we're still continuing to combine and put together things that we've been learning throughout the semester. So as we go through these slides, you'll see some things that are familiar, so we'll review them as we incorporate them into new things. So why do we analyze maps? So these tell us a lot about the current weather happening. The surface plot that you guys looked at whenever you were doing the activity, this is just one example of those. So, and they're analyzed at all vertical levels of the atmosphere. So at the surface, all the way up to the top of the atmosphere, like at 250 millibars. And each level can tell us something different that is important about the forecast. And then we start with what is observed, and then from there we can contour the data. So if you've ever seen a contour map, you can make the same type of maps in meteorology. And contours tell us a lot about weather patterns because it just shows where everything is. So it's kind of similar to what y'all were doing a couple weeks ago with the pressure gradient stuff, but you can do this with pretty much anything. So so a few things on the map. Like I said, you're already familiar with a few of these. We'll go through these. So isotherms, these are lines of constant temperature. This is a mouthful right here. Isodrothotherms, these are lines of constant dew point. So instead of temperature, constant dew point. Isobars, you guys are familiar with this, lines of equal pressure. Remember, they're usually in 4 millibar intervals. Isohypes or isoheights might be called either one of these. These are lines of constant geopotential height. And then an isotac, this is a line of constant wind speed. And then streamlines, these begin at upwind direction and end where the wind shifts abruptly. So whenever you draw these, you need to make sure that the directional arrows follow the flow. Okay, so remember isotherms. These are lines of equal temperatures, and this is just an example of a contour map with drawing isotherms. So if you were given a map like this and I asked you to draw isotherms or lines of constant temperature, then this is how you would get started with this. So sometimes doing this, as you'll see within doing this like in real time sometimes can get like pretty complicated if you have like cold fronts and warm fronts and stuff all over the map. It can make the temperatures all across the country really different. So you may have really crazy lines, but as you can see on this one, the weather is not too crazy. So it just has like a gradual increase or decrease in temperature as you go north, obviously. So anyways, you usually do this in intervals of 5 or 10 degrees, but for the most part, you guys are going to be doing 10-degree differences. But if it's specific, but depending on what the range is and what part of the map you're doing, it may ask you to do intervals for every 5 degrees. So make sure you do know whether you're supposed to do intervals every 10 degrees or every 20 or 5 degrees. So this map right here, it does it with every 10 degrees. So you can either there's really like no specific way to do this. You can either start from the lower temperatures, start from the higher temperatures, or start in the middle. But if you want to start from the lower temperatures, then you'll start at 10 degrees. So you draw a 10-degree isotherm line right here, because when you draw this, the temperatures above 10 degrees are outside of this isotherm, and then temperatures below 10 degrees are inside this isotherm. And then you see the same thing with 20 degrees. So this divides the temperatures in the teens from the temperatures in the 20s. And as you can see, sometimes these isotherms can stretch a long ways across the country. And then the next, you see 30, so it divides the temperatures from the 20s for the temperatures in the 30s. And then the same thing with the 40s. And depending on how close a temperature is to the isotherm, that determines the position of the isotherm. So for example, right here, right over here in Illinois, or wherever this is, I think this is Iowa, this is 22 degrees. And then the isotherm right here is 20 degrees. But if the temperature right here was 20 degrees, then the isotherm would extend it down here, include that, and then loop back over there. So you'll see in the next one that we do, you do the same thing, but you can also do them for smaller ones. So like, for example, since this one is only from 4 to 9 degrees, you have the isotherms for each temperature. So you actually include them. So for the 4 degrees, it actually goes through all the 4-degree temperature points. And then the same thing for 5, and then 6 and 7, 8, 9 is you get in. So it's, like I said, it's kind of similar to the isobars line of constant pressure, but this is with temperature. Okay, so we can do the same thing here. But as you can see, sometimes you might have temperatures that are like at half a degree value. So you would still do your isotherms, but to do them simpler, you can do with 7, 8, and 9. So we have our 7-degree isotherm right here, and it divides the 6 and the 6.5 degrees from the 7.5 degrees. So if you look at it again, what's above 7.5 is inside, and then what's below 7 degrees is below this isotherm. And then the same thing with 8 degrees and then 9 degrees. Okay, and then so here's another example that that we can do. So so there's a lot going on here. So this is a little bit easier because it's like on the intervals of 10. So all you do is for this one, you would just draw the isotherms through each of the points I just mentioned. So we have our group of 20-degree temperatures right here. So you just draw it through like this. And sometimes, yeah, sometimes whenever you do this, you'll get circles, you may get big lines or whatever. And then so do them for the rest of the temperatures. So our 30-degree values go up from Canada all the way down to New Mexico, and then up back towards Michigan again, and then 40 degrees. And then as you'll see, remember, it's the same concept with the pressure gradient. Whenever these isotherm lines are close together, that means there's a tight temperature gradient. So you'll usually see these along a cold front because there's a big difference between the colder air behind it and then the warmer air in front of it. So that's probably an example of what we see right here. So it's down in the 80s, like over like where we are, but just a few hours to the north, they're in the 30s and the 40s. So that's why the 50, 60, and 70 isotherms are all bunched up because they're in between where this hypothetical cold front would be. And then we have 80 and then 90 over in Florida. And then just a note, depending on how the temperatures are lined up, sometimes you may need to draw multiple isotherms. So for example, right here we have our 50 degrees that goes through the middle of the country, and then we also have another 50-degree isotherm to account for the temperatures along the west coast of the United States. And then the reason why you'll like have this discrepancy sometimes is because, as you'll see later on in the slides, these are all based off of surface plots, and there's not very many surface plots in Mexico as there is in the United States. So you might not have as much data and temperature points to work with to draw these isotherms. Okay, so I don't have the slides or the lines for these drawn right here. So this is one you could try on your own later for practice, but this is for pressure. So just like we did a couple weeks ago with the atmospheric motion line, we're looking at pressure. So remember, the surface plots, you have to convert it to millibars so you're able to look at it easier, or you could hypothetically do the isobar plots the same way, just by looking at the difference between the ones right here. So pressures aren't as even or as constant, I guess, in constant patterns as temperature. So whenever you draw like pressure gradient lines, they'll be a lot more complicated sometimes. But yeah, so this would just ask you to draw a 1012 millibar line through this map right here. Okay, so as I mentioned, we have these surface maps these maps at different levels of the atmosphere. So I'm going to go through these and then talk about what we can find from each of these. So at the surface, or which is usually at 1000 millibars, we plot isobars of constant sea level pressure and surface station plots, so like the temperatures. And then from this, we can find fronts, cold, warm fronts, and then low and high pressure systems. And then at 850 millibars, a little bit higher up in the atmosphere, we plot isotherms and isobars / iso heights. And then with this, we can find warm and cold air advection. So we'll talk about this a little more later on. And then 700 millibars, this is where we plot iso heights, and we can find rising motion, which is it's the omega term if you get like really complicated equations like dynamics and stuff, but yeah, so it's just the rising motion of air, and then relative humidity. That's the other main thing. And then 500 millibars, this is iso heights, and this is where you find the vorticity, which is the measure of spin. And then at the upper levels of the atmosphere, we plot isotax, and these are where you find jet streams and streaks. So a lot of this stuff is like super complicated upper level meteorology stuff. So like, for example, in my class this semester, we're learning a lot about vorticity at the 500 millibar level. So, but yeah, you guys aren't going to have to do anything near that level of complexion, but it's just a good idea to know that we can do these maps at different levels of the atmosphere, and some of the different things that you can find out by looking at maps at different levels. All right, next we're going to look at surface maps. We've already talked about this several times this semester. So this is the Global Weather Observation Network surface stations. So if you look here, this is a map of the world with dots that represent all of these surface plots. So whenever you were doing the activity last week and you had to pull up a surface plot, all the different stations that you saw, these are represented by these dots, and there's different types of them. there's the MEDAR and the TAF surface stations, and then there's NEXRAD. And there's also radiant sonde points, which we'll talk about a little bit later on too. But as you can see, there's a whole bunch of these in North America, so there's a ton of data that that we work with. And then, oh, just the other thing is that whenever they're doing all these observations, if you're looking at them on a global scale, they'll all be measured at the same time everywhere. So every 6 hours in UTC time. So 0, 6, 12, and 18. So so I think we talked about this earlier in the semester, but just a quick review. UTC, that's the global standard time. I think it's like measured for the actual time somewhere in Europe, but just for our purposes in the central time zone here in Texas, whenever we're in daylight savings times, so in the summer, we're 5 hours behind UTC. And then whenever daylight saving times end, so for us, that's in a few weeks during the winter, we're 6 hours behind UTC. So whenever it's 18 UTC, it would be 1300 for us, which is 1 o'clock, which is what about, so it's almost 2 p.m. for us. So if you add 5 hours to that, it would be 1700 UTC. So the main takeaway is that these are all done at the same time everywhere, 0, 6, 12, and 18 UTC. And then this is just a picture of an example of one of the surface weather stations. This is called a automated surface observation station. They're frequently referred to as the acronym ASOS, but they measure a bunch of the things that we'll look at in just a minute, such as temperature, pressure, cloud cover, rainfall rates, and stuff like that. So you guys are familiar with these. Remember, these observations are displayed in a station plot. So remember, they show a bunch of things. The main things that they show are temperature and dew point, show the current weather. We'll look at the symbols again to review these in just a minute. Pressure over here, remember, you have to convert it to, most of the time, if you added 10 before this, then you add a decimal point right here. So this would be 1013.8. So you remember, this is where you either add a 9 or a 10, depending on the pressure. And then we have our wind speed. We just looked at that a couple weeks ago. The direction that it's pointing, that's the direction that the wind is coming from. So we have a wind that's blowing from the northeast at about 20 knots. And then our pressure tendency. So whenever it's like this, that means pressure is falling. And then the circle, that represents cloud cover, how many clouds are in the sky. And then here's the symbols again for the current weather, the different ones for rain, snow, thunder, shower, drizzle, freezing rain, ice pellets, fog, and haze. So I believe you guys are going to look at a couple this week during your lab assignment. And then we didn't talk about this as much whenever we discussed station plots before, but this is the pressure tendency. So whichever direction it's pointing, whether it's up or down or constant, this and the number, this it can be decoded right here. So this shows us whether pressure is rising, whether it's falling, and then whether it's falling steadily, falling constantly, or rising steadily, or rising constantly. And then 4, here the dash, that means there's no pressure change. So this is showing that the direction that the pressure is going, whether the pressure is going down or going up. And then cloud cover, you guys looked at this with your activity last week. So yeah, depending on how much of the circle is shaded, that shows us what the current sky cover is. So since it's full shaded right here, that means it's an overcast sky. And then wind speed, we also talked about this. So here is the decoder again. So remember that the full barbs, that's equal to 10 knots, and then the half barb is equal to 5 knots. And then if you get really high winds, then you'll have the flags, which represents 50 knots. And then just remember, the wind direction is where the winds are coming from. Okay, we're gonna switch gears a little bit. We're gonna talk about air masses. So air comes from different places, and they each have different characteristics. And these different air masses coming together produce fronts. So we'll take a look at each of these. So continental Arctic. Obviously, this is up closer to the poles, and you have bitterly dry, cold air. So as I mentioned, whenever they come together, they form fronts. So whenever these polar fronts and Arctic fronts from the north push down, that's how we get our cold fronts. So if you ever hear sometimes the meteorologists on TV, they'll be like, oh, we have a Arctic front coming. That means that, I mean, it's not technically like a meteorology term, but they use that to describe whenever you have super cold fronts coming. So whenever they say, oh, we have like an Arctic or a polar blast coming, that means that we'll get like really cold in like the 20s or the 30s. So yeah, and then we have our other polar air masses. So we have maritime polar over here on the west coast, cool and moist. So that's why Seattle, for example, is always cool and rainy. We have continental polar over here in the northern United States, cold and dry air as well. And then maritime polar, so the same thing on the west coast, on the east coast, cool and moist air. And then closer to the tropics, closer to the equator, we have the tropical air masses. So we have maritime tropical along the west coast and the Gulf Coast and the Caribbean. This is warm, moist air. So this is what affects a lot of our weather since we're so close to the Gulf of Mexico. And then over here, West Texas, the southwestern United States and Mexico, this is continental tropic. So this is hot, dry air coming from the deserts that will affect our weather sometimes too. So, and yeah, these are actually all abbreviated. So whenever you're referring to this, like on a map, this would be CA, this would be CP, these would be like MP, for example. So one of the questions on your assignment is actually labeling these different types of air masses. So whenever you do that, you just have to do the, you can just do the initials. You don't have to write out the whole thing. All right, fronts. We've also talked about this a little bit, but remember that a front is a boundary between two different air masses. And to look for these on a map, you look for a sharp temperature gradient. So one of the contour plots that we were looking at, for example, whenever they're all bunched together, that usually indicates that there's a front. And then a moist gradient, and then a wind direction change. Those are also key indicators of fronts as well. So you're probably most familiar with cold fronts and warm fronts, which are represented by blue and red respectively, but we also have stationary and occluded fronts. So we'll take a look at each of these individually. So a cold front, this is a boundary of an advancing mass of cold air. So we like cold fronts because they cool off the temperatures, and the arrows, they always point in the direction that the cold front is traveling. So whenever cold fronts are coming from the north, coming down towards Texas, these triangles will be pointed down as they go down Texas towards our area in College Station, for example. Remember, cold fronts, they're along different masses, cold and warm air masses. The cold air is moving forward, and then whenever it interacts with this warm air, remember, warm air rises, so it rises above this cold air, and this is how we get our thunderstorms and rain showers. So this is like whenever we were talking about the cloud types, unfortunately we don't really see these, as I mentioned, too often, but this is like an example of a cumulonimbus cloud whenever we get severe thunderstorms. And so you'll see these a lot along cold fronts. And then next is warm front. So it's the same thing, but it's warm air. So normally you'll see warm fronts back up. So like, for example, whenever like a cold front passes through and it like goes into the Gulf of Mexico, sometimes the front will like reverse and it'll come back as a warm front because the warm air that just like got pushed out back by the cold front, it's coming back towards us. So so this is an advancing mass of warm air. And then it's the same thing. The circles represent that it's the direction that the front is traveling. So it's the same concept as a cold front. Whenever warm air moves forward, it rises above cold air, and then you'll usually have a large area of stratiform precipitation because the cold air is receding as the warm front advances. Okay, and then occluded fronts, these are whenever fronts combine. So as you can see here, have a cold front and then a warm front on Monday, and then on Wednesday they like combine together. So you'll see this with the warm air and the cool air, but then you also have the colder air below it as well. So it's basically a combination of both fronts. These are a little bit more rare, but they do happen from time to time. And then next is a stationary front. So instead of colliding like they do in an occluded front, this is whenever you have two air masses meet, but they do not advance or collide with each other. And this frequently happens whenever both air masses have a small temperature and a pressure gradient between them. So if you have a cold front that's coming through and it's only going to drop the temperature from 85 degrees to 78 degrees, for example, that's not a very big gradient. So because there's not that big gradient, you don't have as much pressure pushing the front through, so you'll often see these like back up to each other and then stall out. So this is what a stationary front is, and it has both the cold front and the warm front symbols. And then so yeah, this visualizes it as well. The fronts stall out next to each other, and then a lot of times you'll get rain and sometimes even thunderstorms as these two air masses are next to each other. Okay, next we're going to look at upper air maps. At upper level maps, at any height of a given pressure level, so for example, at 850 millibars, 700 millibars, 500 millibars, 300, or even higher up into the atmosphere, 200 millibars, the height varies with temperature and density. So this is kind of confusing, but this is just the way it is. So the way height is measured varies from at different points in the atmosphere. So whenever you're doing your activity, you're definitely going to want to reference this table a lot. So it's kind of similar to the pressure values on the surface spots where you kind of have to decode them. You kind of have to do the same thing here. So at 850 millibars, this is, you look at the last three digits. So if it says 390, this means it's at 13,900 millibars. So that's almost 1.4 kilometers. And then the same thing at 700 millibars. It's also the last three digits. So it's kind of the same thing. It's the pressure where you have to decode it and look at which one sounds more reasonable. So if it's 885, this would be 2885 meters, or if it's 079, then that would be 3079 meters. And then for 500 and 300 millibars, so in like the middle levels of the atmosphere, this is the first three digits that tells you what height it's at. So 551, our first three digits, 551, and then you add a 0 at the end. So this would be over 5,500 meters. And then the same thing with 911, this would be over 9,100 meters. And then for 200 millibars, which is the very top of the atmosphere, since you're even higher, you use the middle three digits. So we have 152, and then you add a 1 and then a 0 at the end. So this is 11,520 meters. And then the other things on here are the same. So we have our wind barbs and then the temperature and dew point. But again, make sure, because right here, these are in Celsius, so just make sure you're looking at the temperature in the right unit. Okay, and then 850 millibars. So we're gonna look to find where we should put the warm and cold fronts. So remember, we have to look at where the warm air and cold air advection, which right here, we have our labels right here, and look to find these where these are on the map. So remember that a cold air advection, this is the process in which the wind blows from a region of cold air to a region of warmer air. And then warm air advection, it's the opposite. So warm air advection is the process in which wind blows from a region of warm air to a region of cooler air. So we use these to help find our fronts. So first, you're gonna identify the areas of a cold air advection and warm air advection on an 850 millibar map. And then next, you're gonna find the leading edge of the CAA and then the back edge of the WAA. So this shows you where the cold and warm fronts are on a 1,000 millibar map. But remember, we're looking at this at an 850 millibar map. Does anybody know why that is?
Is it because it's closer to the surface?
Yeah, so well, the 1,000 millibars, so that's closer to the surface, so you're not able to see some of the patterns as much. So we go up a little bit higher into the atmosphere at 850 millibars, and this allows us to see the warm and cold air advection, which is sometimes harder to see on surface maps because you can definitely see the advection on the 850 millibar map. So right here we have an 150 millibar map, and we're going to go ahead and find our cold air advection and our warm air advection. So I'll give you a few seconds just to think and guess where both of these would be before I reveal it. Okay, so right over here, you see we have our cold air advection and then the areas of warm air advection based on the direction that the wind barbs are going. So right here in this area, you see this is our cold air advection because if you look at the wind barbs, these are all northerly, northeasterly winds, and it's blowing from an area of colder air. So remember, the wind barbs are the direction that the wind is coming from. So wind is all coming from this way along. So yeah, so you'll see here in just a minute, we'll label our front. And then the warm air advection is the same thing, but the wind barbs are coming from the opposite direction. So it's coming from the direction where we have warmer temperatures. So now that we have these areas, we have to find the leading edge of the cold air advection and the back edge of the warm air advection. So this will show us where our fronts are. So the leading edge of the cold air advection is down here at the bottom. So this is our front passing through. And then we have the same thing over here with the warm front backing up along this area. And then we have an occluded front right here up in Canada off of this cold front and then this warm front. And then you take those off. So whenever you look at the surface map, you just have the fronts listed with the high and low pressure systems and then the isobars. So now that we put all these together, as you can see, there's also another front over here off this low pressure system, the coast of Canada. Now we have a pretty good looking surface map. Okay, and then these aren't as important, so we're just gonna go through these a little bit, but you can see the same patterns at 700 and 500 millibar levels. So as you can see here, we still have a dip in the jet stream right here, and you can still see the same pattern with the wind barbs. So in the upper levels of the atmosphere, the winds are a lot more stronger. So that's why you'll see that these wind barbs often have flags on them, but it's the same. We can still see the same patterns, especially at the 250 millibar. It's very distinct to find where these fronts are. Okay, so I know that was kind of a lot, but that's all for this week. So This week you're going to be doing the weather map analysis from your lab book. I think it's technically the 9th one in your book, but this is the 10th week, 10th lab, so this is going to be called lab number 10. So anyways, it's the weather map analysis lab. Yeah, it starts on page 101. And then if you're doing this, if you have the physical copy of the lab manual, use a pencil whenever you're drawing the isolines, because it's a lot of, until you like get the hang of it, you're going to be erasing a lot until you find where the isolines are. So if you're drawing it on paper, then use it in pencil so you can erase. But for those of you that do the digital version, you're able to erase your work anyway. So yeah, so just be prepared to erase the isolines as you trace them through to find the different lines of constant temperature. And you're going to do all of the problems, or excuse, up through 19, except for number 9. If you go to number 9 on page 112, you'll see there's 6 different parts on there. You don't have to do D through F. So on number 9, only do A, B, and C. And then you'll go through number 19. So yeah, you'll do the whole, all of the questions except for 9, D, E, and F. And then you don't have to do a review question this time either. And then it's due at the beginning of next week's class as normal. And if you have any questions about the assignments, then you can email me or come to my office hours. Does anybody have any questions over the material this week? Awesome. Unless you guys have any questions, you guys are free to go. The slides for this week and the assignment, they should already be uploaded onto eCampus. I'm going to catch up on grading this weekend, but if you guys have any questions about your grade or anything like that, or with the activity, please reach out to me and let me know. But yeah, unless you guys have any questions or anything else, I will see you all next week.
Thank you, Jacob.
Thanks, guys.